This is Pedro, and Pedro is going to tell us about Rust audio and music programming.
Hello, everyone. Good afternoon. And I'll talk about Rust audio programming. So this would be audio programming in the context of building some kind of music, performance, production tools like a guitar effect or something like that. And I'm Pedro. I'm mostly a web developer, UI kind of front-end developer. But I'll talk about audio programming and Rust. So this content is kind of derived from some learnings I had from doing hobby projects, open source that is up on GitHub, mostly during kind of COVID lockdowns. And so on my GitHub, there is this small repository with a bunch of crates that try to build upon some of the existing libraries in Rust, and they have I built front ends or explored front ends in using different approaches. So on this slide, there is a SwiftUI front end, there is a toy looper application, there are some iced front ends for the same looper and for a VST host for development, and a Flutter metronome that is published. The two on the both sides are published, and did some web GUI experiments. And this year, I was working on some just on C++ plugins that are featured there, but aren't really Rust. So what I wanted to talk about is some kind of digital audio intro, really quick, and then Cpal, which is a library for setting up the audio callback, and then some real-time constraints and some solutions or potential solutions, and then just mention very briefly the plugin aspect of this, and some UI development notes. So we want to process sound signals that are these continuous signals, and in order to process them digitally, they need to be discretized. So at a certain fixed time interval, your sound card will take samples out of the audio signal, and the digital representation of the audio is going to be this stream of numbers or samples that goes on kind of indefinitely at the sampling rate. And then while we could process one or two samples at a time, on some contexts, usually there's some sort of buffering. So the sound card will read a certain number of samples onto a buffer, and it will hand it over to the software, and then you process it while the kind of previous buffer is being output. And this will go on indefinitely. And for each buffer, you have certain fixed amount of time to process. So you have a deadline to run processing over that buffer. And if this deadline is missed, then there will be a buffer underrun, which is the audio equivalent to a frame drop, except it will be a lot more noticeable than a frame drop. And so it's kind of unacceptable. So Cpal is a Rust library for cross-platform audio I/O. So it is just wrapping the different APIs for different environments like Windows, Linux, macOS, iOS, and also web audio, which is pretty cool. And this is kind of full example of the setup codes. At the top of this file, there is a host declaration. The host would be kind of the audio driver. There's an output device being declared. That would be the speaker or something like that. Here's just the default. In an app, maybe you would let the user pick the output device. Then you declare some stream configuration, which is the number of channels, sample rate, and the size of the buffer for this output device. And also in a real app, maybe you'd have to negotiate because you have to check what the output device actually supports. Then you create the stream object, which is, as long as it's around, there's going to be audio output. And to create that stream object, you pass in a process function, which is really all you kind of care about. This is an example of process function, generates a sine wave. There are a few issues with that sine wave generation, I think. Like the phase should be wrapping around itself, not just keeping incrementing, but really, I think I just wanted to say on this slide that the Cpal audio buffers are interleaved, which means that the channels are, there's an array of samples and the channels are coming in one after the other, which is different to a non-interleaved representation where you have 2 pointers for, or multiple pointers for every channel. And then I suppose most of the time you actually want to copy this into a non-interleaved representation, because then when you use iterator APIs or whatnot, you probably get a little bit better performance, or maybe. Okay, so then, whoops. So then there are these real-time constraints. So because we have this fixed deadline to run process, then we can't really do any work that takes a non-deterministic amount of time to complete on that process callback. For example, we can't do I/O on the audio thread. We can't take locks, or we can't wait for events to happen, and we can't allocate or deallocate memory, or do any unbounded work, like if there's some person presses a button to stop recording, and now you've kind of accumulated a bunch of samples on a fairly long audio buffer. You don't want to like actually go through all of that audio on the audio callback. Then I put some, and you can see how this memory allocation and the allocation guideline aligns with language like Rust, or languages with lower level kind of memory control, because you need to have control of when that is happening. So there are lots of good resources on this. In particular, from the Audio Developers Conference, or ADC, which is related to a C++ framework called Juice. I put here Pete Goodlife's The Golden Rules of Audio Programming and How to Break Them, and Ross Benzina's Time Waits for Nothing essay. And then there's also a talk there from Timur Domler that is titled Using Locks in Real-Time Audio Processing Safely. And in this talk, he's pretty much describing how you could write a kind of spin lock, sort of, that would be real-time safe, and going over why you can't really even do try lock on the audio thread. So the solutions for this would be, for this constraint, would be to do on other threads and communicate the results. You want to use lock-free data structures and patterns where possible. So if the data is really small, like a gain parameter, like just a number, then you can rely on atomics. If the data is larger, or you need to update it transactionally, then you can either use message passing via lock-free queue, or you can use a pointer swap kind of pattern that I'll show. And either way, you have to solve a memory reclamation pattern, which is where you free the data, where you drop. So what there would be is that you have some shared data between the UI thread and process callback, and you're going to share it through some kind of smart pointer, like let's say like something that looks like ARC. But the problem is that if the UI thread then drops the reference, and then later the audio thread also isn't using that piece of data, then you're going to drop it on the audio thread, and you don't really want it to be dropped on the audio thread. So instead, what you would want it to happen is you would want that kind of shared pointer to be transferred to some other thread that will do cleanup. And there is an implementation of this by Mika Johnston or Glowcoil on GitHub. He implemented a library it's a crate called BaseDrop that implements this idea. So you have this kind of collector object, and then you have smart pointers. So shared is like RC, but when it's dropped, it doesn't get dropped. It just gets pushed to log-free linked list, and then when you call collector.collect, then it's actually going to get dropped. So this way you can control where it gets dropped and when. I did a small little wrapper around this that pretty much just wraps the collector as a singleton, spawns a thread for it, and then it gives you like some utility functions to create the references, and there's like some pooling approach to collecting them. The probably isn't the best, but yeah, I think there is a lot of garbage, like a lot of deallocation going on. So then if you had like some gain parameter or something, you would create a atomic wrapper on that, and then you would wrap it with these share smart pointers in some way, so that you can transfer them between the threads. And there is no atomic F32 in the Rust standard library, so this atomic F32 is something I took from the VST crate, and it's just fake. It just has get and set, and it's a wrapper on another type that has the same size. I think the most general pattern probably is doing message passing with the audio thread, because you, on lots of the time, you don't really want to swap the data under the audio thread. You would want to maybe be able to do a crossfade or so between like the audio graph change or even a filter coefficient change. And so this is code from one of the apps, and then there's some message that gets sent to the other thread, and when the callback starts, then the processor will drain that message queue and do whatever it needs to do with the message. This is using ring buff, which is a ring buffer implementation that is on crates.io. I ported a so ring buff works great. It's just single producer, single consumer. I ported a C++ lock-free queue that is multi-producer, multi-consumer, but don't know how sound that is. So maybe don't trust it for anything super important, but to steal kind of Juice story, that is the author of Juice joke. Maybe there's some musician playing a keyboard, and once every million times they press a note and it doesn't ring, and they won't even know that it was you, or so then the pointer swap thing is that you have some, and this is on base drop. There's a shared cell type that holds a reference to the shared, and you can have the process function will get the reference counted object out of the cell, and other threads can go and make the cell point at something else, and like just swap where it's pointing to, and then the next time that like on the next process callback, the other thread will get the new reference, and the old reference can get collected. There's a crate called a certain lock that you can kind of wrap wrap the process callback with, and then that will replace it replaces the allocator, and then if you allocate inside of that block, it will panic or it will log, so you can have tests and check that you aren't really allocating. And there's also something that was announced on this year ADC, I think, a sanitizer for C and C++ that will do this check, but also do checks for system calls locks. Then I just wanted to mention that you have your software, and you maybe rewrite and run it standalone with Cpal, but you also want it to run as a plugin, and then when you run it as a plugin, you are hosted in some larger piece of software, and the host is calling your audio callback, and the host is hosting your UI. So it just gives you a void pointer to the NS window or UI window or whatever the window is, and you render in there, but you don't really control the event loop, and then this causes some issues with the UI crates. So you just wanted to implement process, but you have all of that code. So I was looking at doing this. What if you had traits for audio processors? And there are people, there are other implementations of this. So this is a trait for audio processors. You have a prepare method where that will be called with the audio settings, and you can use to pre-allocate buffers to all these things. And then there is a process callback method that gets called with the mutable audio buffer, and you just write to that. And I added this audio context structure so that I could stash more things into there later on. Initially, this wasn't really there. I was just passing the audio settings. So there's more things that you might want to pass in, like the transport state, like where you are in the song or the tempo or something like that. Then if you implement these traits, there are some helpers. You can just call this audio processor main function will generate CLI tool for you that you can go and process online and do a listening test, or cross a file and listen to the file, or pass through a MIDI file through your processor if it implements the MIDI processing through it. And you can also run it in case you actually want to write an application. Then there's a missing thing, but you could also generate the VST plugin, and if you have VST plugin, then you need the host needs to introspect into the parameters. So this was a way with procedural macros to try to generate this kind of introspection into the parameters and some associated metadata. Okay, so I tried to do a bunch of things with UI development on this repository, and the first thing I was looking at was web UI. So this is you'd host some web view, and then you'd have some message channel with the Rust app. I did 2 transports with WK message handlers and with WebSockets. But now I think actually WebSockets is probably enough, and you should probably use that. But I think going back to that plugin issue, because you're running in this hosted environment, then lots of the crates don't really work because a lot of the Rust UI ecosystem, or the windowing crates, they need to take control of the event loop, and they need to be main, and they don't really work otherwise. So I had this just raw wrapper on top of WebKit, and Output is a commercial plugin that's built with this approach in C++. They presented how they are doing this with message handlers and HTTP. Then I tried some iced. I think the only notable thing with iced is that, same issue. You don't really have you can't really use iced normal shell, because if you use iced, then the windowing library will take control of the event loop, so you can't really use it. So someone, I guess Billy DM, wrote this iced-based view crate, which lets you use base view, which is windowing library that he wrote, that can be used in this environment because it doesn't take control of the event loop. You can just attach it to a window pointer and it will work, and attach the event listeners in the right way. But then, this ICE crate is pretty much fork of ICE. It just duplicates a bunch of the ICE code. So when there's ICE upgrade, you have to update this entire crate pretty much. And then there's some Rust and SwiftUI and Flutter things with Rust. I think SwiftUI could be used. I will end. So sorry. So just a wrap up is there are these real-time constraints. You have a lot of extra work due to that. You can probably simplify things with message passing and with the reference counting smart pointers from base drop. There are some crates for standalone apps like Cpal and Medir that have been working all right. I think they're fairly immature compared to more like the C++ commercial libraries, but they're pretty good, and they're much nicer to set up and so on. They're great for building plugin formats like VST. There's no audio unit crate or wrapper code, but maybe they'll improve. And there's other projects doing very similar things. Mine is like a learning project, so anyway. Okay, and then I think you should consider using Juice, which is a C++ framework for plugins, for at least some wrapping code, because it will fix some packaging issues just to get it published if you were writing a plugin. And for the DSP code, I've really fond of some other environments that maybe allow for interactive development of the effects. So I really like MaxMSP, which is this node-based programming language, and then they recently released Rainbow, which can do code gen. So you can build your plugin in this way, and then like your audio stuff, and then generate code, and yeah. Okay, so that's it. Yeah, thanks.
Thanks, Pedro. Quick question regarding the real-time constraints and dropping memory. Like I've not done any real-time stuff myself, but I'm wondering, do you have any numbers or any explanation on how much resources it actually takes to drop smaller data structures? Because in my head, I guess I'm thinking well, a bunch of atomic operations to swap out some memory or push into a lock-free queue. Is that really cheaper than dropping, say, I don't know, 20 bytes of heap memory or something? Why is not dropping memory actually such a big problem if it's not 10 megabytes?
No, I don't know. Yeah, I think it's more about being non-deterministic than taking too long, but yeah. You could have very, very small buffer, and then you don't really have much time to have a couple milliseconds or a millisecond. But yeah, yes.
It sounds like you have audio experience in both Rust and C++. Did you feel that the Rust safety helped you out here, or did it get in the way?
I think Rust is much nicer to work with, has package manager, can break things, you have testing and so on. Yeah, I'm not. I don't know. I think I'm not a professional audio developer. I'm not a professional audio developer. So yeah, I think there are some things with the generics and maybe for very simple doing just sharing of atomic, maybe it's a little bit annoying to have to wrappers or to go through some hurdles, but there's you also get macros that can help with a lot of the more syntax noise parts. So yeah, I don't know.
Yeah, so I tried writing a VST once in Rust, and it was a while ago, a year ago, and I was I want to do it for fun, and it's either Rust or nothing. And at the time, it seemed like it was very buggy and not mature enough. How mature do you think it is now to do end-to-end Rust plugin development?
Not very mature.
Okay. It's still not mature. That's it.
I have one question. Sorry. So you must have a comedy around for any kind of Rust audio stuff. Could you point us newbies and more who actually has done audio stuff in here in the audience? So we have a couple of people. So everybody's a newbies. Yay, that's great. So what about comedy? So where people, hey, I'm interested in doing audio programming, but where to start? Where's the comedy around?
Oh, yeah, so this Cpal crate is part of Rust Audio GitHub organization, and then there's a Discord channel with all of these people, and yeah, you can join Discord, chat with them for Rust in particular. Yeah.
Awesome. Thank you, Pedro.